Acids and bases are electrolytes. This means they are able to conduct electricity. Conductivity depends on ion concentration. We are able to indicate whether something is an acid or a base with an indicator. One example is phenolphthalein, which is pink in a base and colorless in an acid.
Acids and bases neutralize each other in solution. For example, the general formula of a neutralization reaction is you have an acid plus a base, and it yields the products of a salt and a water. And when you have either a strong acid and a strong base in solution, the general products are just water, because the H plus ion and the OH ion come from the acids just to form the general formula of the water. For an example of a general neutralization reaction, you have a strong acid of HCl plus a strong base of NaOH, and since they're very strong, they completely dissociate in solution. So the H plus ion from the HCl and the OH negative ion from NaOH comes together to form the water, and the resulting Na plus and Cl negative come to form the salt of NaCl.
An acid-base titration is used to determine molar concentration of an unknown acid or base by completing an acid-base neutralization. In order to conduct a titration, the volume of the unknown substance is measured, and an acid-base indicator is added. Then, a burette is used to add the standardized solution. After, a color change will eventually occur, and this indicates the endpoint of the titration. Finally, you will record the volume of the unknown in the molarity of standard solution, and at the end, you calculate the molarity of the unknown.
The Lewis acid-base theory follows the theory of how acids and bases interact with electron pairs. A Lewis acid is a species that can accept a pair of electrons from another species, so therefore it's an electron pair acceptor, while the base is the species that can donate the pair of electrons to an acid, for example, so it's an electron pair donor. An example of a Lewis acid is H+, whereas for a base it's OH negative or the hydroxide ion.
In the Arrhenius acid-base theory, Arrhenius acids yield hydrogen ions as positive ions in an aqueous solution, while Arrhenius bases yield hydroxide ions as the only negative ions in an aqueous solution. In the process of a neutralization, an Arrhenius acid and an Arrhenius base react to form a salt and water.
The Bronson-Lowry acid-base theory is a continuation or an extension of the Arrhenius theory. And Bronson-Lowry acid is a species that can donate a proton to another species, so it's basically a proton donor. And the proton that is donated from, for example, an HCl ion donates a proton to an H2O molecule, which forms the hydronium ion, and the hydronium is what gives the acid's properties. And for a base, it's a proton acceptor. So what happens is, for example, NH3, it accepts the proton from the acid in the reaction, which, for example, you have NH3 plus H2O. It accepts the H plus from the H2O to form NH4 plus, and the resulting extra hydroxide ion is left over.
A common acronym often associated with the Bronsted-Lowry theory is bases accept, acids donate, which shows that acids donate protons and bases accept protons. The pH scale is a scale of acidity and basicity based on the hydronium ion concentration in aqueous solutions. It goes from a scale of 1 to 14.
Whereas on the flip side, the pOH is a scale of acidity and basicity based on the hydroxide ion concentration in aqueous solution. So the general pH scale is as follows. When an acid goes from the range of the number 1 to 6, while a base goes from the number 8 to 14. Now in the middle, the neutral 7 is where the concentration of the H3O plus and the OH negative ions are equal, which is usually your water. The acidity of an acid usually increases with a lower number because the hydronium concentration is the largest. So for your strong acids like HCl or HNO3, the hydronium concentration is really high, so the number is usually lower as compared to like a weak acid such as HF, which has a higher pH. For a base, it's the opposite. The larger the number, the larger the hydroxide concentration. Therefore, like a NaOH has a greater concentration of hydroxide ions as compared to a weaker base, such as ammonia or NH3. So the sodium hydroxide will have a larger pH due to the more excess of hydroxide ions as compared to the NH3.
Using the pH scale and the pH scale, we can find either the pH or the pOH. For example, if you have a pH of 6, you can find the pOH by subtracting 6 from 14 and get a pOH of 8.
So for example, a reaction indicating a pH decrease, which is usually when it goes from a higher to a lower, is the reaction nitrogen dioxide plus water, which yields HNO3, which is a very strong acid. So the NO2 acts as the base and the H2 acts as the water, which forms this very strong acid of HNO3. Now on the flip side, a reaction indicating a pH increase from a lower to a higher number is the reaction 2NaOCl plus water, which yields 2NaOH plus 2OCl negative. The formation of the sodium hydroxide indicates a increase in the pH because the hydroxide ion concentration is increasing, therefore the pH is increasing, so the number is getting larger.
It is imperative,
Very extremely imperative,
to know the 7 strong acids in chemistry. The first strong acid is HCl.
hydrochloric acid,
The second strong acid is HNO3.
nitric acid,
The third, HI.
hydroiodic acid,
The fourth one, HBr.
bromic acid,
The fifth one, HClO3.
hypochlorite acid,
The sixth one, HClO4.
hypochlorite acid,
And finally, H2SO4.
sulfuric acid.
Along with knowing the 7 strong acids, it is very important to know the strong bases. Strong bases are usually group 1 metals and big group 2 metals. For example, calcium down and a hydroxide.
For example, for a group 1, you can have like an NaOH or lithium hydroxide thing kind of going on. And for the group 2, you can have like calcium hydroxide, strontium hydroxide. It is imperative to note that when you are working with elements in group 2 that there is an oxidation state of 2+. So when you form or take a calcium and a hydroxide, there's going to be 2 hydroxides due to the transfer of the 2+.
Review questions.
The correct answer is choice B, fewer hydroxide ions and hydronium ions. This is because HCl is a very strong acid, and the hydronium concentration has to be larger than the hydroxide concentration. Therefore, there's going to be more hydronium ions than hydroxide ions. With this, the pH is going to be extremely low.
The correct answer is B, barium hydroxide. This is because you can immediately eliminate choice C and D, which are both strong acids. Then it leaves you with choice A and B. A is then eliminated because it is a weak base and leaves you with choice B, barium hydroxide.
The correct answer is choice 4, pink with phenolphthalein. In this question, you can eliminate choice 1 immediately because a solution will never be colorless when you're testing with litmus paper. So, for example, blue litmus paper turns red under acidic conditions, and red litmus paper turns blue under basic conditions, so therefore it's never going to be colorless. Which then leads you to eliminate choice 2 because a pH of 12 indicates a basic solution, so it won't be red, it will be blue. So you're left with choice 3 and 4. And phenolphthalein is colorless in acidic solutions, therefore the correct answer is choice 4.